In the dim glow of early 20th century laboratories, when humanity was just beginning to grasp the invisible threads that held the universe together, one man looked beyond the limits of sight and reason. His name was Niels Bohr, a Danish physicist whose quiet determination and fearless imagination would transform not only how scientists saw the atom, but how humanity perceived reality itself. The world of science at that time was standing at a crossroads. The elegant laws of Isaac Newton had long described the dance of planets, the motion of falling apples, and the mechanics of machines. Yet, deep inside the atom, in the mysterious realm too small for even the finest instruments, those same laws began to crumble. Something strange and unseen ruled there. Electrons did not move like tiny planets orbiting a sun. Instead, they seemed to vanish and reappear, behaving as if governed by rules that no one could yet explain. It was in this age of confusion and discovery that Niels Bohr emerged, carrying with him not only the tools of a scientist but the vision of a philosopher. Born in Copenhagen in 1885, Bohr grew up surrounded by intellectual curiosity. His father, a physiologist, encouraged debate and questioning, while his mother came from a family rich in education and culture. The young Bohr learned early that truth was not something handed down by authority, but something earned through relentless inquiry. He studied at the University of Copenhagen, where his fascination with physics quickly evolved into an obsession with understanding the atom, that mysterious particle thought to be the smallest building block of matter. By the early 1900s, scientists knew that the atom was not indivisible as once believed. Experiments by J.J. Thomson had revealed the existence of electrons, tiny negatively charged particles embedded within a positive framework. Later, Ernest Rutherford's famous gold foil experiment shattered the idea of a solid atomic sphere. Instead, he revealed that almost all the atom's mass was concentrated in a dense central nucleus, surrounded by a cloud of electrons. This model, while revolutionary, had one major flaw: it couldn't explain why atoms were stable. According to classical physics, those orbiting electrons should have lost energy, spiraled inward, and collapsed into the nucleus. But atoms clearly didn't do that. Something was missing. Something beyond the reach of Newton's world. Bohr entered this puzzle like a detective chasing a trail of hidden clues. In 1913, he introduced an idea that seemed almost magical. What if electrons didn't move in any orbit they pleased? What if their motion was restricted to specific, fixed energy levels, discrete paths that followed the rules of quantum mechanics rather than classical physics? This idea, simple yet profound, became the foundation of the Bohr model of the atom. In Bohr's universe, electrons could only exist in certain allowed orbits around the nucleus. When they jumped from one orbit to another, they absorbed or released energy in the form of light, a concept that beautifully explained the mysterious patterns in atomic spectra that had baffled scientists for years. This vision was radical. It went against centuries of accepted thought. Classical physics had always assumed that nature behaved continuously, like the smooth flowing of water or the steady ticking of a clock. Bohr's proposal shattered that continuity. He introduced the notion of quantization, the idea that energy came in indivisible packets, called quanta. Electrons could not glide smoothly between energy levels, they had to leap. And in those leaps, Bohr saw the key to atomic stability. The electrons remained in their defined orbits without radiating energy, and only when they changed their orbits did they emit or absorb light. The universe, Bohr suggested, was not a machine wound by predictable gears. It was a dance of probabilities and discrete steps. At first, many scientists resisted Bohr's vision. It seemed too abstract, too philosophical. The idea that electrons could somehow choose certain orbits and ignore others went against the mechanical logic that had dominated science for centuries. But slowly, evidence began to build in his favor. The spectral lines of hydrogen, long a mystery, matched perfectly with the energy differences predicted by Bohr's model. Each color of light emitted by hydrogen corresponded to a specific jump between energy levels. For the first time, The strange beauty of atomic light could be mathematically explained. This was not just a triumph of theory. It was a revolution in thought. Bohr had shown that the universe at its smallest scales did not obey the same rules as the universe we see. His atomic model was a bridge between two worlds, the predictable realm of classical physics and the mysterious domain of quantum phenomena. It revealed that the atom was not a miniature solar system, but a structure governed by entirely new laws that would later evolve into the full framework of quantum mechanics. As Bohr's ideas spread across Europe, they ignited a new generation of thinkers. Physicists like Werner Heisenberg, Erwin Schrödinger, and Wolfgang Pauli built upon his foundations, expanding quantum theory into a vast and intricate landscape. But even among these great minds, Bohr stood apart, not just for his scientific insight, but for his philosophical depth. He understood that his model was not the final truth, but a stepping stone toward a deeper understanding. He once said, "Every great and deep difficulty bears in itself its own solution. It forces us to change our thinking in order to find it." That was precisely what his atomic model demanded, a complete change in the way humanity thought about nature. In a sense, Bohr's work was not just about atoms, it was about the limits of human knowledge. The electron, once thought to be a simple particle, became a symbol of mystery. Was it a particle or a wave or something beyond both? Bohr believed that the answer depended on how one observed it, a revolutionary idea that later became central to the Copenhagen interpretation of quantum mechanics. But even before that interpretation took form, his 1913 model had already cracked open the door to a new reality, one where uncertainty, duality, and probability ruled. The impact of Bohr's vision rippled far beyond physics. It influenced chemistry, explaining why elements behaved the way they did and why they formed bonds in specific patterns. It shaped the study of light, radiation, and energy. And ultimately, it laid the groundwork for the quantum revolution that would give birth to technologies like semiconductors, lasers, and quantum computing. Without Bohr's bold step, much of modern science and technology might never have been possible. Yet, Bohr was not a man driven by ambition or fame. Those who knew him described him as gentle, thoughtful, and deeply humble, a man who preferred conversation to confrontation and ideas to glory. In his institute in Copenhagen, young scientists from around the world would gather to discuss, debate, and challenge one another. Bohr encouraged open dialogue, often sitting quietly and listening before offering a simple question that would transform the entire discussion. He believed that truth was best discovered collectively through dialogue and doubt, not dogma. In this way, the Bohr model became more than a scientific theory, it became a symbol of intellectual courage. It taught humanity that understanding the universe required us to abandon old certainties and embrace the unknown. Bohr's electrons were not mere symbols of matter. They were emblems of curiosity itself, forever orbiting the nucleus of truth, but never collapsing into it. His model demonstrated that progress comes not from clinging to familiar ideas, but from daring to imagine what lies beyond them. As decades passed, new discoveries refined and replaced parts of Bohr's model. Schrödinger's wave mechanics and Heisenberg's uncertainty principle revealed that electrons could not be pinned down in exact orbits after all. They existed in clouds of probability, described by mathematical wave functions rather than fixed paths. But even as the details changed, the essence of Bohr's insight endured. The atom was a quantum system, not a miniature mechanical one. Every evolution in physics since then has carried the imprint of his original vision. Looking back, one might say that Bohr did for the atom what Copernicus did for the cosmos. He displaced humanity from its comfortable assumptions and placed it in a universe far more complex and wondrous than anyone had imagined. Just as Copernicus showed that Earth was not the center of creation, Bohr revealed that the atom was not a tiny clockwork sphere, but a dynamic, unpredictable world ruled by strange and elegant laws. And just as Copernicus opened the way for modern astronomy, Bohr opened the way for quantum theory. the science that would redefine not only physics, but the very nature of knowledge. To appreciate the scale of Bohr's achievement, one must imagine the courage it took to propose such an idea. In 1913, quantum theory was still in its infancy. Max Planck had only recently introduced the concept of energy quanta to explain blackbody radiation, and Albert Einstein had applied it to light to explain the photoelectric effect. But no one had yet dared to apply these ideas to the atom itself, to the structure of matter at its core. Bohr's decision to do so was a leap into the unknown, a daring synthesis of ideas that others thought incompatible. And yet it worked. His equations matched observation with precision, and his model became the foundation upon which the entire edifice of quantum physics was built. There is something deeply poetic about Bohr's discovery. It reminds us that even in the smallest things, the universe reveals its grandest mysteries. The atom, once seen as a simple building block, became a universe within a universe, a realm of energy, vibration, and transformation. In that microscopic dance of electrons, Bohr saw the reflection of a greater truth, that reality is layered, complex, and endlessly surprising. His atomic model was not just a scientific tool, it was a philosophical statement about the nature of existence. That the deeper we look into the world, the less it conforms to our expectations. When Bohr published his theory, the scientific community was stunned. Some called it brilliant, others called it absurd. But over time, experiment after experiment confirmed his predictions. The spectral lines of hydrogen, helium, and other elements lined up perfectly with Bohr's calculations. The model's elegance and accuracy made it irresistible. It was a triumph not only of intellect but of imagination, the kind of leap that defines human progress. As the years passed, Bohr's influence spread across continents and generations. His atomic model became the cornerstone of education in physics, a gateway through which every student of science would pass. But beyond its pedagogical value, it carried a deeper message: that knowledge is not static but ever evolving, and that each discovery is a doorway to new questions. Bohr himself often said that the opposite of a profound truth is not a falsehood, but another profound truth. That paradox, that contradiction lies at the heart of understanding, became the guiding principle of quantum thought. Bohr's revolutionary atomic model transformed our view of matter, not by providing all the answers, but by revealing how limited our answers had been. It forced humanity to reimagine what matter even meant: not solid, not stable, but a symphony of energies held in delicate balance. The electron, once a simple speck of charge, became a dynamic participant in a cosmic dance of probabilities. In Bohr's hands, the atom was no longer a lifeless structure, it was alive with motion, energy, and possibility. The story of Niels Bohr did not end with the unveiling of his atomic model. In many ways, it was only beginning. The ripples of his vision spread outward like waves from a single stone dropped into an infinite sea of ideas. Across the scientific world, thinkers were awakening to the realization that the universe was not the tidy clockwork they had imagined. Bohr's model had thrown open the door to the quantum realm, and what lay beyond that door was at once wondrous and unsettling. The rules that governed the atom seemed to belong to a world of dreams and paradoxes, where certainty dissolved into probability and observation itself became a creative act. It was as though humanity had finally peered behind the curtain of nature, only to discover that the stage was far more mysterious than anyone had dared to believe. In the years that followed, Bohr refined his ideas while mentoring a generation of scientists who would carry the quantum revolution forward. Among them was a young German physicist named Werner Heisenberg. Under Bohr's guidance, Heisenberg developed the uncertainty principle, a concept that complemented Bohr's vision perfectly. It declared that certain properties of a particle, its position and momentum, could never be known simultaneously with perfect precision. The more one knew about one, the less one could know about the other. This was not a flaw in measurement, it was a fundamental feature of reality. For Bohr, this principle was not a limitation of science, but a revelation about nature itself. The world was not built on deterministic certainty, as Newton had believed, but on an intricate balance of possibilities. Bohr's response to Heisenberg's discovery was the concept of complementarity. He proposed that the behavior of electrons, and indeed all quantum entities, could be understood only through mutually exclusive yet complementary perspectives. Sometimes the electron behaved like a particle, at other times like a wave, and both descriptions were necessary to form a complete picture. Reality, Bohr insisted, could not be reduced to a single viewpoint. Just as light could act as both wave and particle, truth could exist in multiple, interdependent forms. This idea, born in the crucible of atomic theory, soon found echoes in philosophy, psychology, and even art. Bohr's atom had become a metaphor for the complexity of knowledge itself. The Copenhagen interpretation, forged through long nights of debate in Bohr's Institute, became the philosophical heart of quantum mechanics. It asserted that quantum systems do not possess definite properties until they are observed. Measurement does not simply reveal reality, it participates in its creation. For many, this was an unsettling thought, one that challenged the very notion of an objective universe. Einstein famously resisted it, declaring, "God does not play dice with the universe." Bohr, ever calm and reflective, replied, "Einstein, stop telling God what to do." Their exchanges were legendary, representing two different visions of nature, Einstein's deterministic cosmos and Bohr's probabilistic one. Yet, even amid disagreement, there was respect. Each understood that the other was seeking the same truth from a different angle, and that tension drove physics to greater depths. As Bohr's philosophical reach expanded, so did the practical impact of his ideas. Quantum mechanics, once a realm of pure abstraction, began to yield concrete results. The understanding of atomic structure revolutionized chemistry, allowing scientists to predict how atoms combine to form molecules. The periodic table, once a patchwork of empirical observations, became an elegant expression of quantum rules. Spectroscopy, electronics, and later solid-state physics all grew from the seeds Bohr had planted when the transistor was invented in the mid-20th century, enabling the digital revolution. It did so upon principles that traced back to Bohr's atomic vision. Every computer chip, every laser beam, every MRI scanner owes a silent debt to those first quantum orbits. Yet Bohr himself remained uninterested in wealth or glory. His passion lay in understanding. During the Second World War, when nuclear research turned deadly, Bohr's moral strength was tested. He was forced to flee Nazi-occupied Denmark, eventually reaching the United States, where he contributed to scientific discussions that would lead to the atomic bomb. But he also became one of the earliest voices urging for international cooperation and control of nuclear weapons. He saw in the atom both creation and destruction, the ultimate duality of knowledge. After the war, he returned to Copenhagen and devoted himself to promoting peaceful uses of atomic energy. His vision had always been one of enlightenment, not annihilation. The power hidden within the atom, he believed, should serve humanity's progress, not its downfall. What makes Bohr's transformation of our view of matter so extraordinary is that it transcended science. Before Bohr, matter was seen as solid, passive, and predictable, a collection of particles obeying mechanical laws. After Bohr, matter became dynamic, interactive, and deeply connected to observation and meaning. The electron was no longer a simple bead of charge but a quantum entity whose existence unfolded through relationships. Reality, it seemed, was not an independent stage upon which events occurred, but a living web woven from the act of measurement itself. This redefinition of matter changed not only physics, but the philosophical foundations of human thought. It blurred the line between subject and object, reminding us that the observer and the observed are entwined in ways far deeper than our senses reveal. Through the lens of Bohr's model, the universe became a place of participation. To observe an electron was to engage in a cosmic conversation, to influence the very phenomenon one sought to understand. In a world where every experiment reshaped the system it measured, certainty became an illusion. Yet, rather than despair, Bohr found beauty in this uncertainty. He saw it as a reflection of nature's harmony, a balance between knowledge and mystery. His favorite symbol, which he later incorporated into his coat of arms when knighted, was the yin and yang of Chinese philosophy, representing the unity of opposites. Beneath it, he placed the words contraria sunt complementa. Opposites are complementary. It was the essence of his life's work, distilled into a single phrase. As decades passed, quantum theory continued to evolve. New discoveries, from quantum entanglement to the standard model of particle physics, built upon the framework Bohr had helped establish. Each breakthrough confirmed the depth of his insight. When physicists discovered that entangled particles could remain connected across vast distances, it seemed to echo Bohr's belief in the holistic nature of quantum systems. Even as experiments grew more precise and mathematics more complex, the philosophical questions Bohr raised persisted. What is reality? Does the universe exist independently of observation, or is consciousness somehow woven into its fabric? Such questions may never have definitive answers, yet they remain the legacy of Bohr's revolution, a reminder that science is not only about finding answers, but also about learning to ask better questions. The cultural impact of Bohr's ideas was equally profound. Writers, artists, and thinkers began to draw inspiration from the strange, poetic logic of the quantum world. Modernist literature embraced uncertainty and multiplicity. Painters sought to capture energy and motion rather than static form. Even psychology felt the tremors of quantum thought as scholars explored the interplay between perception and reality. Bohr's atom became a symbol of a new age, an age in which truth was no longer singular but layered, relative, and ever-changing. To understand matter was to understand ourselves complex, contradictory, and forever in motion. In classrooms around the world, the Bohr model became a child's first glimpse into the quantum universe. Though simplified, it carried a sense of wonder that no textbook could diminish. The idea that electrons jump between levels of energy captured imaginations, turning invisible physics into a vivid dance of light and motion. Even as more advanced theories replaced the original model, teachers kept using it, not because it was perfectly accurate, but because it was perfectly inspiring. It told a story that could be grasped by the human mind, a story in which energy and matter played out a cosmic choreography. Bohr had given science a language of images, a way to speak about the unseen. Behind all this stood the man himself, gentle, reflective, often lost in thought. Visitors to his institute recalled the quiet intensity of his presence. Conversations with Bohr could be bewildering. He spoke slowly, circling an idea as if testing its strength from every angle. But once he found the right words, they cut straight to the heart of the matter. He encouraged students to think freely, to challenge even his own theories. His institute became a sanctuary of intellectual openness, where young minds could explore without fear. In that environment, ideas blossomed like sparks in a storm. Many who studied under Bohr went on to win Nobel Prizes themselves, carrying his influence across generations. The transformation Bohr began continues to unfold today. In laboratories around the world, scientists manipulate individual atoms, trap electrons in quantum dots, and build machines that exploit superposition and entanglement. Quantum computers, devices that compute by harnessing the strange logic of the quantum realm, stand as living testaments to Bohr's vision. These machines do not process information in binary yes or no bits but in quantum states that can be both at once. Their power comes directly from the principles Bohr helped reveal more than a century ago. The once abstract dream of understanding the atom has become the engine of a new technological era. But Bohr's greatest gift may not lie in the technologies derived from his theories. It lies in the humility his vision instilled. He taught scientists, and humanity at large, that knowledge has boundaries, and that those boundaries are not walls but doorways. The universe is not something to be conquered or fully understood, it is something to be approached with respect and curiosity. In the interplay of energy and uncertainty, Bohr saw a reflection of life itself, dynamic, unpredictable, yet profoundly ordered. His work reminded us that the search for truth is not about final answers, but about the endless expansion of understanding. If one listens closely, the echoes of Bohr's revolution can still be heard in every field of human inquiry. In philosophy, where questions of perception and reality intertwine; in art, where abstraction mirrors the unseen world; in technology, where quantum mechanics drives progress; even in the ethics of science, where Bohr's plea for responsibility in the atomic age remains as urgent as ever. His model of the atom may have been refined and surpassed, but his way of thinking endures, a way that embraces paradox, welcomes uncertainty, and finds harmony in contradiction. Imagine, then, the atom as Bohr saw it, a tiny solar system of energy, pulsing with rhythm and possibility. Each electron moving not in random chaos but in quantized grace, shifting between states like notes in a cosmic symphony. Light flashes out as electrons leap from orbit to orbit, and with each flash, the secrets of the universe whisper to those who listen. In that whisper lies the story of every element, every molecule, every spark of life. The vision that Bohr gave us was not merely scientific, it was poetic, a vision of unity hidden within diversity, of simplicity born from mystery. Today, when we split atoms or harness their energy for medicine and technology, we are living within Bohr's legacy. His model taught us to see matter not as inert substance, but as a living pattern of energy and interaction. It reshaped how we understand not only atoms but galaxies, stars, and even ourselves. From the vastness of space to the smallest particle, the same quantum principles weave the tapestry of existence. Bohr's insight, that nature is both knowable and elusive, both orderly and uncertain, remains a guiding light in the ongoing quest to understand reality. As the century turned and new generations of scientists looked deeper into the quantum realm, they continued to find themselves standing in Bohr's shadow. The electron, once a mystery, is now understood as part of a field that spans the universe. Yet, the essence of Bohr's message endures, that knowledge and mystery are two sides of the same coin. To study the electron is to touch the infinite. To measure it is to become part of its story. And in that realization, science and philosophy meet. Niels Bohr's revolutionary atomic model transformed our view of matter by revealing that matter is not a thing but a process. A dance of energy, probability, and meaning. It broke the illusion of solidity and replaced it with a vision of interconnection. It showed that the smallest particle holds within it the logic of the cosmos, and that the act of understanding changes both the observer and the observed. Through his courage, humility, and insight, Bohr invited humanity to step beyond certainty into wonder. The camera pans out from the laboratory lights of Copenhagen, where a young physicist once traced equations on a chalkboard, to the boundless night sky above. Each star burns with the same atomic fire that Bohr sought to understand. The same quantum leaps that animate electrons in an atom ignite the fusion in distant suns. The micro and the macro are mirrors of each other, connected through the laws he helped reveal. In the soft glow of those stars, Bohr's vision lives on, a reminder that within every atom lies a universe, and within every question, the promise of discovery. And so the story continues. The journey that began with a single idea, that electrons occupy discrete energy levels, has unfolded into an epic of exploration that still shapes our world. Bohr's name may belong to history, but his spirit belongs to the future. For every new scientist who gazes into the quantum realm, every thinker who embraces uncertainty, and every dreamer who believes that reality is more mysterious than it seems, carries forward the flame first lit in that quiet Copenhagen laboratory. Niels Bohr taught us that to understand matter is to understand ourselves, and that beyond every answer lies another horizon, waiting to be seen. In the closing years of the 19th century, the world of physics stood firm on the grand pillars laid down by Newton and Maxwell. Nature, it seemed, was an elegant machine governed by clear, deterministic laws. Every planet's motion, every ripple of light, every swing of a pendulum could be traced, measured, and predicted. To most scientists of the age, The universe was complete, its mysteries tamed by mathematics and reason. Yet, in the shadow of that confidence, a quiet rebellion was beginning to stir. Small, subtle experiments began to reveal cracks in the classical world, and at the center of those cracks danced a single, elusive figure, the electron. Discovered by J.J. Thomson in 1897, the electron was the first subatomic particle ever identified, a fragment of matter so tiny it defied comprehension. At first, it seemed like a simple discovery, one that neatly fitted into the growing framework of atomic science. But as physicists began to study its behavior, they found something deeply unsettling. The electron did not behave like any known object in the universe. It was both a particle and something else. Something ghostly, something that refused to obey the rules of classical physics. The journey to understand this strange entity would soon dismantle centuries of certainty and give birth to a new science, the quantum theory. At the dawn of the 20th century, a few visionary minds sensed that the laws of the small would not mirror the laws of the large. Among them was Max Planck, a German physicist who, in 1900, made a desperate mathematical assumption to explain an experimental anomaly known as blackbody radiation. Planck suggested that energy was not continuous but emitted in discrete packets, or quanta. He did not yet know it, but with that idea, he had cracked open the door to the quantum world. His equation worked, but it introduced a concept so radical that even he doubted its physical meaning. The idea of quantized energy seemed absurd to the classical mind, yet it would soon become the key to understanding the electron's mysterious behavior. When Albert Einstein entered the stage in 1905, he carried Planck's quantum seed into new territory. By explaining the photoelectric effect, the way light can knock electrons off a metal surface, Einstein proposed that light itself was made of quanta, tiny packets of energy later called photons. This revelation turned physics upside down. Light, which had long been known to behave as a wave, now appeared to behave like a particle. And the electron, which had been treated as a particle, began to show wave-like characteristics in return. The very categories that had defined physics for centuries were dissolving. The stage was set for the most profound reimagining of reality in human history. In laboratories around the world, scientists watched the electron's strange behavior unfold. When beams of electrons passed through thin metal foils or slits, they created interference patterns, the signature of waves. Yet, when observed directly, the same electrons struck detectors like solid particles. This dual nature, wave and particle, continuous and discrete, defied logic. It seemed that the electron could not decide what it wanted to be until someone looked at it. And that realization hinted at something deeper. That observation itself was part of the physical process. The universe was not a stage upon which matter performed. The observer was part of the performance. It was this enigma that drew the attention of Niels Bohr. When Bohr developed his atomic model in 1913, he did so to explain why electrons did not simply collapse into the nucleus as classical physics predicted. His solution, quantized energy levels, provided the first concrete evidence that the electron's motion obeyed quantum rules. The electron could occupy only specific orbits, each with a fixed energy, and when it jumped between these orbits, it emitted or absorbed energy in discrete amounts. This was the beginning of a new understanding. The electron was not merely a particle circling a nucleus but a quantum being, existing in a realm where energy, position, and motion were all intertwined. Bohr's model explained the spectral lines of hydrogen with astonishing precision. The beautiful colors emitted by gases, when heated, were not random. They were the fingerprints of electrons leaping between energy states. For the first time, the invisible dance of electrons could be connected to the visible light of the universe. But Bohr's model was only the beginning. As experimental tools improved, scientists realized that the electron's behavior could not be fully captured by orbits alone. Its movements were not confined to precise paths, but spread across regions of probability. The atom, once imagined as a miniature solar system, now resembled a cloud of possibilities. In 1924, a young French aristocrat named Louis de Broglie proposed a daring idea that deepened the mystery. If light could behave like a particle, perhaps particles like electrons could behave like waves. His hypothesis, simple yet revolutionary, suggested that every moving particle had an associated wavelength, a wave of matter itself. Soon after, experiments confirmed his prediction. Electrons fired through crystals produced interference patterns just like waves of light. This discovery marked the birth of wave-particle duality, a concept that would become one of the central pillars of quantum theory. The electron was no longer just a point in space, but a wave of probability, existing in many places at once until measured. The understanding of the electron's wave nature transformed the study of matter. In 1926, Erwin Schrödinger formulated his famous wave equation, describing how the electron's wave function evolved over time. This mathematical masterpiece provided a complete framework for predicting the behavior of electrons within atoms. But it also introduced a profound philosophical challenge. The wave function did not describe a physical wave in space, but a wave of probability, a map of potential realities. The electron was not at a single location until observed. Instead, it existed as a spread of possibilities. Observation did not merely reveal the electron's position, it determined it. Werner Heisenberg soon followed with his uncertainty principle, asserting that it was impossible to know both the exact position and momentum of an electron simultaneously. The more precisely one was measured, the less precisely the other could be known. This was not a limitation of technology, but a law of nature itself. The electron could not be pinned down because it did not have definite properties independent of observation. Reality at the quantum level was not solid and absolute but fluid and probabilistic. The universe, once viewed as a grand machine, now appeared as a dynamic web of potential outcomes shaped by chance and measurement. These revelations shook the foundations of physics. The electron's behavior had forced scientists to abandon determinism, the belief that every effect has a definite cause, and replace it with a new logic based on probability. The classical vision of the cosmos, predictable and ordered, gave way to one that was uncertain yet profoundly interconnected. Quantum theory emerged as the new language of nature, capable of explaining phenomena that classical physics could not even describe. The electron had become both messenger and mystery, the bridge between the visible and invisible, the key to unlocking the quantum world. The implications of this new understanding were immense. Quantum mechanics, built upon the behavior of the electron, became the foundation for all modern physics. It explained why atoms form stable structures, why chemical reactions occur, why matter emits light, and why energy behaves in discrete quanta. From semiconductors to superconductors, from lasers to quantum computers, every breakthrough of the modern age traces its roots to that first, strange realization that the electron does not follow classical paths but quantum laws. The technology that powers the modern world, computers, smartphones, satellites, all exists because the electron does not move the way Newton thought it should. But beyond the mathematics and machines, the electron's behavior introduced a deeper philosophical shift. It blurred the boundary between object and observer, between knowledge and reality. In the quantum realm, the act of measuring alters what is measured. This was the heart of Bohr's Copenhagen interpretation that physical systems do not have definite properties until observed. It was a statement that unsettled Einstein, who famously protested, "Do you really believe the moon exists only when you look at it?" Yet, experiment after experiment confirmed that at the quantum level, Bohr and his colleagues were right. The universe was not a passive entity waiting to be described, it was participatory, its reality unfolding through interaction. In the language of the quantum world, certainty was replaced by probability and cause by correlation. Electrons could tunnel through barriers, appear in places they should not be, and influence each other across vast distances through entanglement. The very concept of locality, the idea that objects are affected only by their immediate surroundings, began to dissolve. The behavior of a single electron could no longer be understood in isolation. It had to be seen as part of a larger system, connected by invisible threads of quantum interaction. What began as an attempt to understand a simple particle had revealed the interconnected fabric of reality itself. As scientists explored deeper, they found that the electron was not just a building block of matter, but a cosmic storyteller. Its movements and transitions gave birth to the light of stars, the chemistry of life, and the circuitry of thought. Every chemical bond, every spark of electricity, every flash of color in the universe arises from the quantum leaps of electrons. The same processes that power the sun's fusion reactions also animate the neurons in the human brain. In this sense, the electron is the bridge between the cosmos and consciousness, the thread that connects the stars to the mind that studies them. In the laboratories of the 20th century, as quantum mechanics matured, the electron became a tool as well as a mystery. Electron microscopes revealed worlds within worlds, imaging structures smaller than light could ever show. Quantum tunneling allowed devices to sense and amplify signals at unimaginable precision. Even today, as scientists venture into the field of quantum computing, it is the manipulation of electrons, their spins, states, and entanglements, that lies at the heart of progress. The same strange rules that once defied understanding now serve as the blueprint for technology. Yet, for all our mastery, the electron retains its aura of mystery. Even now, physicists debate what it truly is, a particle, a wave, or something beyond both. When we calculate its properties, we find that it behaves as if it has no size, no substructure, no internal parts. It is both point-like and infinite, simple and complex. Some theories suggest that the electron might be a vibration in a deeper quantum field, a ripple in the fabric of space itself. Others propose that its existence hints at hidden dimensions or new symmetries yet to be discovered. Whatever the answer, the electron continues to remind humanity that understanding is never final. As we look back across the century of discovery, we see that the electron's behavior did more than introduce quantum theory. It transformed human thought. It taught us that nature is not built from certainty, but from patterns of possibility. It revealed that reality is not something fixed, but something that emerges through observation and interaction. It invited us to see the universe not as a rigid machine, but as a living, breathing mystery, one that responds to inquiry with both answers and more profound questions. The electron, in its quiet, invisible motion, became the herald of a new era, an era where science learned to dance with uncertainty, where knowledge became humility, and where the boundaries between matter and meaning began to blur. Through its strange behavior, the electron taught humanity that the smallest things often carry the greatest truths, and that the foundation of all reality lies not in solidity, but in vibration, not in certainty, but in wonder. The electron's tale did not end with Bohr, Schrödinger, and Heisenberg. It only began to deepen, expanding into a web that stretched across every field of human understanding. Once the foundations of quantum theory were laid, a new generation of thinkers rose to explore the strange consequences. In laboratories filled with the hum of vacuum tubes and glowing cathode rays, the quantum world revealed its language, a language not of certainties but of amplitudes, probabilities, and entanglement. The electron, once a mere component of the atom, had become the ambassador of a new cosmos, a cosmos built not on objects, but on interactions, relationships, and information. In this new world, equations no longer described solid paths through space, they described evolving waves of possibility. The wave function, that ghostly mathematical expression first imagined by Schrödinger, became the centerpiece of the theory. It contained everything that could be known about a system, yet it revealed nothing until measured. The moment of observation, when the wave collapsed into a single outcome, became the most mysterious act in physics. What caused that collapse? Was it consciousness itself, as some dared to imagine? Or was it simply the inevitable interaction of quantum systems with their surroundings? The debate continues to this day. each viewpoint offering a different vision of reality, yet all born from the same enigma, the behavior of the electron. Through the lens of this theory, matter was no longer seen as a collection of tiny balls colliding in the void, but as vibrations of quantum fields. The electron became a ripple in the electron field, existing everywhere at once until disturbed. When a particle appeared in a detector, it was not a small object arriving at a place. It was the universe itself responding to a question. The field, invisible and continuous, underlies everything we see, and the electron, through its behavior, revealed that the world we experience is but the surface of a deeper, more unified reality. In the 1930s, as quantum mechanics matured, its strange precision began to astonish even its creators. When physicists calculated the properties of hydrogen using quantum equations, the results matched experimental data to extraordinary accuracy, within fractions of a percent. This precision was unlike anything in science before. The theory's predictions worked, even when no one could fully agree on what the theory meant. In the hands of Paul Dirac, the mathematics of the electron went even further. Dirac's equation not only described the electron's motion, but predicted something no one had imagined: the existence of its mirror image, the positron, a particle of the same mass but opposite charge. A few years later it was found in cosmic rays, confirming that the strange world of equations could unveil realities beyond imagination. The electron had thus revealed a new symmetry of nature. For every particle, an antiparticle must exist. The dance between matter and antimatter became one of the deepest mysteries of the universe, and it all began with the humble electron. Its behavior had opened a door not just to understanding atoms, but to reimagining the cosmos itself. The quantum theory born from its motion became the cornerstone of particle physics, leading eventually to the discovery of quarks, gluons, and the vast structure of the Standard Model. Yet, even amid this expanding panorama of subatomic life, the electron retained its central place. It was the simplest and most familiar quantum being, the guide that led physicists through the labyrinth of the microscopic world. The practical consequences of understanding the electron's quantum behavior soon transformed the 20th century. When scientists realized that electrons could exist in discrete energy states inside solids, they began to explore how those states could be controlled. This led to the invention of the transistor, a tiny switch that could amplify or control electrical signals, the heart of all modern electronics. The transistor, developed in 1947 by John Bardeen, William Shockley, and Walter Brattain, ushered in the information age. From radios to computers, from satellites to smartphones, every digital device today is a monument to the quantum nature of electrons. Each bit of data stored, each signal transmitted, each pixel lit on a screen is a whisper of quantum physics, a testament to the electron's dual existence as both wave and particle. Soon, quantum mechanics gave rise to the theory of semiconductors, the foundation of modern computing. Engineers learned to harness the probabilistic motion of electrons within crystals, creating circuits so small that millions could fit on a fingernail. In lasers, electrons jumping between energy levels emit coherent light that can cut steel or carry the world's internet traffic through fiber optic cables. In superconductors, electrons pair up in quantum harmony, flowing without resistance through wires cooled to near absolute zero. Everywhere, the same principle repeats. By understanding how electrons behave at the quantum level, humanity gained the power to reshape the macroscopic world. Yet, the deeper the mastery, the greater the mystery became. The more precisely scientists could measure the electron, the more they realized how strange it was. Quantum electrodynamics, or QED, developed by Richard Feynman, Julian Schwinger, and Sin-Adaro Tominaga, became the most accurate theory ever created. It described how electrons and photons interact, accounting for every subtle effect, from the electron's magnetic moment to the tiny shifts in energy levels known as the Lamb shift. The agreement between QED's predictions and experiments reached astonishing precision: 1 part in a trillion. It was as if nature herself had written her laws in the language of quantum fields, and the electron was her most articulate expression. Feynman, with his playful genius, often compared the electron to a storyteller whispering secrets about the universe. In his diagrams, the paths of electrons twisted and turned through space, time, exchanging photons, looping back into themselves, creating and annihilating virtual pairs. Each line on the page represented an infinite sum of possibilities, all the paths the electron could take, all the interactions it could have. The universe, at its core, was not deterministic but statistical, a grand symphony of probabilities adding up to the world we observe. The electron's behavior was not chaos but patterned uncertainty, a harmony born from chance. This new worldview began to seep beyond physics, influencing philosophy, art, and even spirituality. The rigid walls between subject and object, mind and matter, began to blur. If the observer affects what is observed, then perhaps consciousness itself is woven into the fabric of the cosmos. Poets, philosophers, and scientists alike began to see parallels between quantum indeterminacy and the mysteries of human perception. In this sense, the electron became a metaphor for existence, elusive, dual, unpredictable, yet profoundly interconnected. But science did not stop at metaphor. As the 20th century gave way to the 21st, the quantum behavior of electrons became the frontier of technology once again. Quantum computing emerged from the realization that an electron's spin, its tiny intrinsic magnetism, could represent not just a zero or a one, but both at once, through superposition. By entangling multiple electrons, scientists could perform computations that would take classical machines millions of years. The dream of quantum supremacy, solving problems beyond the reach of ordinary computers, rests on controlling electrons with unimaginable precision, coaxing them to dance in perfect quantum rhythm. Quantum sensors, quantum cryptography, and quantum communication networks all build upon the same foundation. By exploiting the fragile coherence of electron states, humans now touch the edge of a new technological era, one where information and matter merge. The future of science may not lie in smashing particles together, but in listening to the quiet whispers of electrons entangled across space, a future where distance becomes irrelevant and knowledge flows at the speed of thought. And still, behind every equation and every experiment, the same truth resonates. The behavior of the electron introduced not just the foundation of quantum theory, but the foundation of the future itself. Yet amid all this triumph, the philosophical riddle remains unresolved. What is the electron really? Is it a point, a wave, or a pattern of probabilities? Does it exist independently of observation, or does it spring into being only when measured? Experiments continue to blur the line. The double-slit experiment, now performed with single electrons, still produces interference patterns, even when electrons pass through the apparatus one at a time. Each electron seems to interfere with itself, as if aware of all possible paths. But when detectors are placed to determine which slit it goes through, the interference vanishes, and the electron behaves like a classical particle. The act of asking the question changes the answer. Nature responds not with fixed truth but with context-dependent reality. Some physicists, seeking to escape this paradox, propose the many worlds interpretation, that every quantum event splits the universe into countless parallel realities, each containing one of the possible outcomes. In one world, the electron passes through the left slit, in another, through the right. Every choice, every measurement, every act of observation births a new branch of existence. Others, like Bohm, sought hidden variables, unseen causes that restore determinism beneath the quantum veil. And yet, despite decades of exploration, no hidden mechanism has ever been found. The universe appears to be fundamentally probabilistic, its smallest components guided not by certainty but by possibility. And so the electron, through its behavior, continues to teach humility. It reminds us that reality may be stranger than imagination, that knowledge itself has limits. The quantum revolution it sparked was not merely scientific but existential. It forced humanity to confront the idea that what we call real might depend on how we look. It replaced the mechanical universe of Newton with a participatory cosmos, alive with potential. The electron's behavior was not just an anomaly to be explained. It was a message that the ultimate nature of reality cannot be separated from the act of awareness. Even the largest structures in the universe, galaxies, stars, life itself, owe their existence to this quantum behavior. The stability of atoms, the formation of molecules, the burning of stars, all arise from the laws discovered through the electron. The carbon in our bodies, forged in the hearts of stars, carries within it the same quantum leaps that once baffled Bohr. The light from distant galaxies, stretching across the void, is the testimony of electrons transitioning between energy states eons ago. Every photon that reaches our eyes, every breath we take, every heartbeat, every thought, all are threads woven from the same quantum fabric, and so, the story of the electron is the story of everything. From the first spark of Planck's quanta to the intricate patterns of Schrödinger's waves, from Bohr's orbiting electrons to Feynman's dancing diagrams, the journey has revealed that the universe is not a clockwork but a conversation, an eternal dialogue between possibility and perception. The electron's behavior introduced the foundation of quantum theory, but in doing so, it also introduced a new way of seeing the world as a realm of interconnected mysteries, where knowledge is never complete and wonder never ends. When we switch on a light, when we send a message across the world, when we gaze at the stars, we are engaging with the same quantum processes that shaped the birth of physics itself. The hum of electricity in our homes, the glow of screens, the pulse of technology, all are manifestations of the quantum symphony first heard in the whispers of electrons. The very civilization we inhabit is a monument to the smallest particle's strange behavior. The invisible dance of electrons sustains the visible world, and through it, the human spirit has learned to ask deeper questions about existence. As science advances toward quantum gravity, dark matter, and the mysteries of the multiverse, the electron remains our faithful guide, a reminder that even the simplest things conceal infinite depth. Its discovery did not just change physics, it changed the human narrative. The behavior of the electron shattered the illusion of certainty, introduced the beauty of probability, and revealed the profound unity of all things. In every spark of lightning, in every circuit, in every atom of the cosmos, the electron continues to whisper the same timeless truth, that the universe, at its heart, is not a machine but a miracle of motion, energy, and possibility. And perhaps that is the final lesson, that the more we learn about the electron, the more we learn about ourselves. For like the electron, we too exist between potential and realization, between the seen and unseen, shaping our reality through observation and choice. We, too, are waves of possibility collapsing into moments of meaning. The quantum world is not separate from us, it is within us. The electron's behavior introduced the foundation of quantum theory, but in its echo, it also introduced the foundation of human curiosity. The endless search to understand not just the universe, but our place within it. In the early decades of the 20th century, when the scientific world stood divided between the certainties of classical mechanics and the mysteries of the atomic realm, one mind dared to see beyond the chaos. Niels Bohr. He was not merely a physicist seeking answers, he was a visionary searching for order within the unseen. To him the universe was not an accident of motion, but a symphony of hidden harmonies, and at the center of that symphony lay the atom, a universe in miniature, simple yet profound, fragile yet eternal. Bohr's great revelation was not simply about the atom structure, but about how energy itself behaved at the smallest scales. His idea of quantized energy levels would change physics forever, explaining why matter was stable and why the universe did not collapse into chaos. At the dawn of the 1900s, scientists knew the atom existed, but its structure was a mystery. J.J. Thomson's discovery of the electron in 1897 had shattered the notion of the atom as indivisible. The electron's presence suggested a complex interior, but no one could explain how it all held together. In 1911, Ernest Rutherford's famous gold foil experiment revealed that almost all of an atom's mass was concentrated in a tiny, dense nucleus, with electrons orbiting far away. This was a revelation. The atom was mostly empty space. But it also introduced a devastating problem. According to classical physics, those orbiting electrons should radiate energy as they moved, spiraling into the nucleus within a fraction of a second. If that were true, all atoms, and everything made of them, should collapse instantly. Yet the world endured, solid and stable. Something was missing from the laws of nature. That missing piece arrived through the mind of Bohr, a young Danish physicist who combined curiosity with courage. He recognized that the atom could not be explained by the rules of classical mechanics. Instead, it required a new principle, one that defied intuition but fit reality. Drawing inspiration from Max Planck's idea that energy comes in discrete packets, or quanta, Bohr proposed something extraordinary. Electrons could orbit the nucleus only in certain allowed paths, each corresponding to a specific energy level. They could not exist in between these levels, just as a piano's keys produce distinct notes with no sounds in between. When an electron jumped from a higher orbit to a lower one, it emitted a quantum of light, a photon, with energy exactly equal to the difference between those levels. This was not speculation. It was a bold, mathematical vision of how the atom could exist without collapsing. Bohr's quantized model transformed the chaotic universe of atomic theory into a structured order. The electrons, instead of being doomed to fall inward, were locked into defined states of stability. These quantized orbits explained why atoms radiated only specific wavelengths of light, the sharp lines observed in atomic spectra that had puzzled scientists for decades. In one elegant theory, Bohr bridged the visible and the invisible, connecting the colors of light emitted by hydrogen to the hidden architecture of the atom. For the first time, the patterns of nature were revealed not as random but as mathematical music, energy expressed in discrete steps, light born from transitions between invisible orbits. The world of physics reacted with both amazement and disbelief. Here was a theory that dared to claim nature was not continuous but quantized. That energy came in indivisible steps, not flowing like water but ticking like a clock. To many, this was an affront to centuries of logic. Yet experiment after experiment confirmed it. The hydrogen spectrum matched Bohr's predictions with astonishing accuracy. Those lines of color, once mysterious, became signatures of energy transitions within the atom, a cosmic barcode of matter itself. What Bohr had given the world was not merely a new model of the atom. He had given it a new way to think about energy, motion, and reality. Bohr's quantized energy levels explained the stability of matter in a way classical physics could never achieve. In the old view, electrons would continuously lose energy, but in Bohr's vision, they were bound by quantized constraints, unable to exist at arbitrary distances or energies. Like planets orbiting their sun along invisible rails, electrons could only occupy the orbits permitted by quantum law. The atom, therefore, was not a fragile system but a perfectly balanced one, governed by discrete harmonies of motion. The universe itself seemed to hum with precision, each atom a microcosm of quantized rhythm. But Bohr's brilliance lay not only in the concept, but in his humility before nature's strangeness. He did not pretend to know why electrons behaved this way. He accepted that the atomic world might obey rules beyond human intuition. To him, physics was not about forcing the universe into familiar shapes, but about listening to its mysterious logic. This philosophical openness became the heart of what would later be called the Copenhagen interpretation, the idea that reality at the quantum level does not exist as a fixed state, but as a range of possibilities, only crystallizing when observed. Bohr's quantized energy levels were the first whisper of that truth. that the universe is not deterministic but probabilistic, not fixed but dynamic. The impact of this idea rippled far beyond the lab. For centuries, philosophers had debated whether reality was continuous or composed of indivisible elements. Bohr's model gave that debate a new dimension. It showed that energy, like matter, was granular, and that the microscopic world operated with its own logic, a logic that was precise yet unpredictable. This duality fascinated both scientists and thinkers. It challenged the belief that the universe was a smooth machine running under Newton's laws, suggesting instead a world that jumped in steps, where change came in leaps, not flows. The elegance of Bohr's model also lay in its universality. Though he built it for hydrogen, its principles echoed through all atoms, forming the foundation of quantum mechanics. When Werner Heisenberg, Erwin Schrödinger, and Paul Dirac extended Bohr's insights, they did so upon the scaffolding of quantized energy levels. Without Bohr's conceptual leap, the entire edifice of modern physics, from quantum field theory to chemistry, might never have risen. It was Bohr who gave the electron a home, who gave the atom stability, and who gave energy its steps. Every spectrum of light in the night sky, every glow of a neon lamp, every star's color is a testament to that discovery. To grasp how profound Bohr's quantization was, one must imagine the world without it. Without discrete energy levels, atoms could not exist as we know them. Electrons would drift continuously, radiating energy until matter collapsed. There would be no stable atoms, no molecules, no chemistry, no life. The quantization of energy is, quite literally, the reason the universe endures. Every breath we take, every spark of sunlight, every bond between atoms is governed by those invisible quantum steps. Bohr's theory was not merely a scientific breakthrough, it was a revelation of existence itself. As Bohr refined his model, he encountered new challenges. His theory explained hydrogen beautifully, but struggled with more complex atoms. It could not fully account for the fine details in spectral lines or the influence of electron spin. Yet rather than diminish his contribution, these challenges inspired a new generation of physicists to go further. Schrödinger's wave mechanics and Heisenberg's matrix formulation were born from the attempt to expand Bohr's ideas into a complete quantum theory. Even as the old orbits disappeared into the abstract mathematics of wave functions, the principle of quantized energy remained at the core. It was Bohr's insight that bound them all. The notion that nature restricts energy to discrete values, that stability arises not from smoothness but from separation. There was a poetic irony in Bohr's vision. By quantizing the atom, he made the universe both more predictable and more mysterious. He solved the problem of stability, but opened the door to uncertainty. The same quantization that explained atomic structure also implied limits on what could be known. For if electrons could only exist in specific energy levels, then their exact positions and velocities could never be determined simultaneously, a truth that Heisenberg would later formalize as the uncertainty principle. Thus, Bohr's quest for atomic stability led not to mechanical certainty but to philosophical wonder. The atom, it turned out, was not a miniature clockwork but a shimmering cloud of probabilities, stable yet uncertain, defined yet elusive. In the quiet of his Copenhagen Institute, Bohr often reflected on the paradoxes his work had revealed. Visitors described him as contemplative, soft-spoken and profoundly thoughtful, always searching for meaning beyond equations. He believed that science and philosophy were not separate but intertwined. That to understand nature, one must also understand the limits of human perception. His quantized atom was not only a model of matter but a mirror of the human condition. A balance between chaos and order, between knowledge and mystery. In the jumps of electrons, Bohr saw the rhythm of the cosmos, a rhythm echoed in thought, life, and creation itself. The experimental confirmation of Bohr's theory brought him international acclaim. Spectroscopists across Europe verified that his formula matched the observed frequencies of hydrogen's spectral lines with stunning precision. The Rydberg constant, once an empirical curiosity, now had a theoretical foundation. For the first time, physics had connected the measurable world of light to the invisible architecture of the atom. The success was so striking that even skeptics had to acknowledge that something profound had occurred. Einstein, though critical of the probabilistic nature of quantum mechanics, admired Bohr's courage and the beauty of his results. Their future debates would define the philosophical boundaries of physics for decades. Bohr's quantized atom became the foundation of chemistry as well. By explaining how electrons occupy distinct shells, it laid the groundwork for understanding the periodic table, why elements behave as they do, why chemical bonds form, and why matter organizes itself in complex ways. Every reaction, every spark, every molecule can trace its logic back to the quantized energy levels Bohr proposed. The world of chemistry, from the structure of DNA to the composition of stars, owes its coherence to the same principle that kept hydrogen's single electron from collapsing into its nucleus. By the 1920s, Bohr's vision had become a bridge between worlds, between the deterministic past and the probabilistic future, between the classical and the quantum. His quantized orbits had served their purpose, evolving into the more sophisticated wave models that would follow. Yet his concept remained the soul of quantum physics, that nature, at its most fundamental level, proceeds in steps, not in continuums. Bohr had shown that stability itself arises from quantization, that the universe's solidity depends on its discreteness. What began as a solution to a simple problem, why atoms don't collapse, had revealed the deepest truth about matter, that the stability of everything depends on the granularity of energy. In that discovery lies a profound message, that even chaos has structure, that randomness hides rhythm, and that the smallest leap of an electron can illuminate the vastness of the cosmos. Bohr's quantized energy levels were more than a mathematical trick. They were the first glimpse into a reality where boundaries are fundamental and where order emerges from constraint. It is because energy comes in steps that stars shine in colors, that metals conduct electricity, that our eyes perceive light. The universe's beauty, from the glow of neon lights to the shimmer of distant galaxies, is the poetry of quantized energy written across time and space. Bohr's insight thus marked a turning point not only in physics, but in human thought. It told us that nature's deepest truths are not continuous symphonies, but discrete notes, each essential to the harmony of existence. In the leap of an electron, Bohr found the secret of stability. In the gap between energy levels, he found the structure of reality itself. The atom was no longer a mystery, it was a masterpiece of quantized design. As the echoes of Bohr's discovery rippled through the corridors of science, the meaning of quantization began to deepen. It was no longer just an idea about how electrons move, it became a window into the secret rhythm of the universe. The concept of quantized energy levels did not only explain atomic stability, it revealed that nature itself is not continuous and smooth, but built from small, indivisible packets of energy, where everything that seems calm hides a pulsating, vibrating structure beneath. It showed that even the quiet stability of matter arises from a balance of motion, a dance of possibilities held in perfect order by mathematical law. Bohr realized that within the atom, stability was not a matter of stillness but of harmony. Electrons were not resting in their orbits, they were moving in precise, quantized states that prevented them from radiating energy continuously. This was astonishing, for classical physics had predicted the opposite, that any charged particle in motion should lose energy over time. But Bohr's model told another story. In his universe, electrons were travelers on defined routes, allowed only certain journeys, and forbidden from taking others. Their energy was not arbitrary, it was sacred, limited to specific values dictated by nature's quantum code. This leap of imagination was so daring that it seemed almost philosophical. Bohr was suggesting that the universe itself chooses where matter can and cannot exist. The world of physics began to stir with debate. Some found Bohr's ideas bewildering. How could energy come in jumps? How could something so fundamental behave in such a discrete and mechanical way? But experiment after experiment began to confirm it. The hydrogen spectrum, long a mystery, matched Bohr's predictions with perfect precision. Each bright line in that spectral pattern was no longer a curiosity. It was the signature of an electron moving between quantized levels, releasing energy as light when it fell and absorbing it when it rose. These spectral lines became the fingerprints of atoms, unique to each element, proving that Bohr's theory was not an illusion but a map of reality. As the theory spread, it inspired others to expand upon its boundaries. The young Werner Heisenberg, bold and brilliant, took Bohr's quantization to new mathematical heights. He transformed the physical model into pure abstraction, matrices, probabilities, and uncertainty, turning Bohr's vision into the language of modern quantum mechanics. Yet, even as the mathematics grew more abstract, Bohr's simple image of quantized orbits retained its charm. It gave scientists a way to visualize the invisible, a story to tell about the architecture of the atom. In Copenhagen, Bohr's Institute became a beacon for young physicists, a sanctuary for minds hungry to explore the quantum unknown. There, under his gentle guidance, ideas collided like atoms, fusing into new insights. He encouraged questions more than answers, believing that science grows not from certainty but from wonder. His notion of quantized energy levels was never a closed door. It was an opening to the infinite complexity of matter. Every atom, in Bohr's eyes, was a miniature universe, governed by laws both strict and mysterious. But the real beauty of Bohr's quantized atom was not just in its scientific power, it was in its philosophical depth. It invited humanity to rethink what it means for something to exist. If an electron could only be found in certain states, if it could leap between energies but never in between, then the nature of existence itself was granular. The universe was no longer a continuous stream, but a mosaic of discrete possibilities. Bohr had unknowingly touched upon a truth that transcended physics, that even the smallest parts of creation obey limits, and within those limits lies stability, identity, and order. This realization changed how scientists viewed light, energy, and motion. It bridged the gap between matter and radiation, revealing that the two were not separate realms, but two faces of the same quantum coin. When an electron dropped from a higher level to a lower one, it emitted light, literally transforming its lost energy into a wave of pure electromagnetic beauty. The universe, then, was not silent. Every atom was a musician, playing notes of light as electrons danced through quantized steps, composing the grand symphony of existence. The simplicity of Bohr's quantization hid a complexity that would take decades to unravel. Later discoveries, such as Schrödinger's wave mechanics, revealed that electrons did not orbit like planets but formed clouds of probability. Yet, even these clouds were still quantized, still bound by Bohr's original idea that energy exists in discrete steps. This shows the power of Bohr's vision. Though the imagery evolved, the core truth remained. Quantization was not a human invention, it was a property of nature itself. As scientists delved deeper, they began to see quantization everywhere. In the vibrations of molecules, in the behavior of solids, in the emission of radiation, even in the structure of stars. The universe seemed to whisper in Bohr's language. Quantum jumps dictated the color of elements, the chemistry of life, the glow of distant galaxies. Without quantized energy levels, atoms would collapse, light would lose meaning, and the universe itself would dissolve into chaos. The stability of the cosmos depended on those invisible rules Bohr first articulated in 1913. In the decades that followed, as physics advanced into nuclear and particle realms, Bohr's influence remained. His model was no longer the final word, but the foundation of all words to come. It gave birth to a scientific culture that valued the unseen as much as the seen, the probabilistic as much as the definite. It taught scientists that reality is not always what it appears to be, that stability can emerge from restriction, and that harmony can arise from rules that seem paradoxical to human intuition. Even in the age of quantum computing and particle accelerators, the concept of quantized energy levels remains central. Quantum bits or qubits rely on discrete states, echoes of Bohr's ancient insight. Lasers, MRI machines, and semiconductors all function because electrons still obey those same quantized steps. The light that powers our world, the devices that connect us, the stars that shine above us, all depend on the principles Bohr first imagined. As Bohr aged, he reflected often on the meaning of his discovery. He understood that physics was not just about equations. It was about human understanding, about the dialogue between the observer and nature. His quantized model of the atom had shown that even the smallest unit of matter is a world of mystery, and that stability is not an absence of change, but a balance of opposing forces. This insight paralleled his philosophical belief in complementarity, the idea that truth can exist in multiple forms, each revealing something essential yet incomplete. The story of Bohr's quantized energy levels is not only the story of an atom, it is the story of how humanity learned to listen to the language of nature. It tells us that order does not come from chaos by accident, but through deep, unseen patterns that hold everything together. Every electron that moves, every photon that shines, every molecule that forms, all obey the quantized rhythm first recognized by Bohr. It is as if the universe hums to an ancient melody, one we are only beginning to hear clearly. When we look at the night sky and see the colors of distant stars, we are witnessing Bohr's legacy. The spectral lines that cut through starlight are fingerprints of quantized transitions, records of electrons leaping between energy levels in atoms light years away. Each hue is a note from the quantum orchestra, proof that the same laws Bohr uncovered on Earth govern the cosmos itself. The stability of atoms and the brilliance of stars are threads of one grand fabric, woven together by quantization. Today, more than a century after Bohr's revolutionary model, scientists continue to push beyond his ideas, exploring quantum fields, entanglement, and particle symmetries. Yet, each new discovery still echoes the same truth, that nature moves in steps, not in slides, in pulses, not in flows. The quantized world Bohr revealed remains the foundation upon which the skyscrapers of modern physics stand. His concept of energy levels was not merely a theory. It was a revelation, a key that unlocked the hidden structure of the universe. And so, the story continues. Each new experiment, each new observation adds another verse to the song Bohr began. The atom remains stable, not because it stands still, but because it dances according to rules older than time. Through Bohr's eyes, we learned that the smallest things in the universe are the most disciplined, and that from their discipline arises the vast, elegant order we call reality. His discovery was not only scientific, it was poetic. It told us that beneath the apparent chaos of existence lies a deep and unbreakable symmetry, a rhythm that gives life its persistence and the cosmos its stability. The electron's path, invisible yet exact, continues to remind us that knowledge is both limited and limitless. We may never see the full picture, but with Bohr's quantization, we glimpse its outline. The atom's calm glow, the star's eternal shimmer, the very breath of the universe, all sing the same truth. Energy moves in steps, and those steps sustain everything that is. In the growing dawn of the quantum age, Niels Bohr stood not as a solitary thinker, but as the center of a constellation of brilliant minds. His strength was not only in his ideas, but in his ability to bring together those who could expand them. The story of quantum theory is not just Bohr's alone. It is the story of collaboration, of intellectual sparks meeting across borders and generations to illuminate the mysterious realm of the subatomic world. Bohr believed that science advanced not through isolation but through dialogue. His Copenhagen Institute became more than a building, it became a living organism of thought, a place where uncertainty was not feared but celebrated as the beginning of understanding. Within its walls, some of the greatest scientific debates in history took place. Werner Heisenberg, a young German physicist, arrived with fresh energy and restless imagination. Under Bohr's mentorship, he transformed abstract ideas about electrons into the foundations of quantum mechanics. It was in Copenhagen that Heisenberg formulated his uncertainty principle, a concept that would forever change the language of science. Bohr challenged him, questioned him, and guided him with the patience of a philosopher and the curiosity of a child. Their discussions often stretched late into the night, circling around the same question: how can we describe a world we cannot see? From those conversations, a new vision emerged, one that united mathematics, observation, and philosophy into a single, elegant framework. Bohr also worked closely with Schrödinger, whose wave equation described the atom not as a mechanical orbit, but as a vibrating field of probability. Though Bohr and Schrödinger disagreed deeply, Bohr favoring the abstract interpretation of measurement and Schrödinger yearning for a clearer physical picture, their conflict became fertile ground for progress. Bohr saw disagreement not as division but as dialogue, believing that truth in quantum mechanics was multi-faceted, that different perspectives could coexist, each revealing part of a greater whole. This idea would later evolve into his principle of complementarity, the notion that seemingly opposite descriptions of reality, such as particle and wave, are both necessary to grasp the full truth of nature. Beyond Europe, Bohr's influence extended to young physicists across the world. He welcomed them to Copenhagen as equals, fostering an atmosphere of trust and intellectual freedom. His openness helped shape the minds of scientists who would later change the world. Men like Wolfgang Pauli, who developed the exclusion principle, and Max Born, who introduced the statistical interpretation of quantum mechanics. Even Albert Einstein, though often skeptical of Bohr's conclusions, engaged in legendary debates with him about the meaning of quantum reality. Their exchanges, Einstein insisting that God does not play dice, and Bohr replying, "Stop telling God what to do," became the poetic symbols of a scientific revolution. These collaborations did more than refine equations, they shaped the very soul of modern physics. Bohr's Institute became the birthplace of quantum culture and environment where imagination was encouraged, and where the boundaries between science and philosophy blurred. He built bridges not only between people but between ideas, between what could be measured and what could be imagined. It was through these connections that quantum mechanics grew from a daring hypothesis into the foundation of our understanding of matter and energy. Even during the darkest years of the 20th century, when war and fear threatened to divide nations, Bohr's collaborative spirit endured. He believed that scientific knowledge belonged to humanity as a whole, and that cooperation was the only path to progress. His later work in advocating for international scientific openness reflected the same ideals that had guided him in physics: the belief that truth cannot flourish behind closed doors. Bohr's collaboration with other physicists expanded not only the quantum framework, but also the human framework of science itself. It showed that the pursuit of knowledge is a collective journey, that no single mind can hold the universe alone. Through the meeting of minds, Bohr, Heisenberg, Schrödinger, Einstein, and others, the strange, invisible world of the quantum became tangible. Each voice added its own rhythm to the great conversation of discovery, and Bohr was its quiet conductor, ensuring that harmony arose from chaos. The legacy of those collaborations still echoes today. Every quantum theory, every experiment, every technological marvel rooted in atomic science owes something to that era of unity and intellectual daring. The foundations of quantum mechanics were not built in silence but in dialogue, in argument, laughter, doubt, and revelation. Bohr's vision thrived because he understood a timeless truth that the greatest discoveries are born when minds meet, challenge, and inspire each other to see beyond the visible. In this way, the electron's mysterious world was not just unlocked by equations, it was revealed by human connection. In the shifting landscape of early 20th century physics, where certainty was giving way to probability, Niels Bohr helped shape a new way of seeing reality. Out of the tension between measurement and mystery emerged what became known as the Copenhagen interpretation, a vision of the quantum world that would redefine not only physics but the philosophy of observation itself. The idea was simple in statement, yet profound in consequence. The act of observing a quantum system changes the very thing being observed. Reality, in the microscopic realm, was not a fixed picture waiting to be discovered. It was a story that unfolded only when we look. In the quiet rooms of Bohr's Institute, this concept took form through countless conversations with young physicists such as Heisenberg and Bohr. The Copenhagen interpretation did not claim to tell what the electron really is, but rather what we can meaningfully say about it. When an electron moves around a nucleus, it exists not as a single point following a clear path, but as a range of possibilities. A cloud of potential locations, each waiting for measurement to define it. Only when the observer measures does one possibility become real. Bohr often explained this through his notion of complementarity, that the wave and particle descriptions of matter are both valid, though they cannot be seen at the same time. Just as light can behave like a wave in one experiment and like a particle in another, nature offers different faces depending on how we ask our questions. This was not just a scientific statement. It was a philosophical revelation. It suggested that knowledge is participatory, that the observer and the observed are entangled in a delicate relationship. Bohr's words carried a quiet humility. He reminded physicists that they were not outside the universe looking in, but part of the process itself. In the quantum realm, to measure is to intervene, to know is to alter. The Copenhagen interpretation replaced the rigid certainty of classical mechanics with a new language of probabilities, forcing scientists to accept that nature cannot be fully pinned down. Instead of solid facts, we find patterns of likelihood. Instead of fixed paths, we find clouds of chance. For some, this was liberation; for others, it was discomfort. Einstein resisted the idea passionately, insisting that God does not play dice. But Bohr saw no recklessness in nature, only subtle order beyond human intuition. He replied that perhaps it was not nature that was uncertain, but our tools of thought. The universe, he believed, speaks in a dialect of probabilities, and understanding it requires us to listen differently. The Copenhagen interpretation became the bridge between what could be measured and what could be imagined, teaching scientists that the limits of knowledge are not failures, but features of reality itself. Through Bohr's influence, a generation of physicists began to view their work not as discovering immutable truths, but as mapping the boundaries of what can be known. Every experiment became a dialogue with the universe, every result a reminder that observation and reality are partners in the same cosmic dance. The flicker of an electron, the burst of a photon, the collapse of a wave function. These were no longer mechanical events, but moments of creation, where possibility crystallized into fact. In this light, the Copenhagen interpretation transcended physics. It reshaped how thinkers, philosophers, and even artists viewed the act of perception. It suggested that meaning itself is conditional, that truth can shift depending on the frame of observation. Bohr's calm insistence that science must respect the limits of what can be said became a form of intellectual ethics, a call to precision, patience, and humility. More than a century later, the echo of Bohr's vision still guides quantum science. Every time a particle is measured, every time a quantum computer performs a calculation, the principles of Copenhagen whisper in the background. They remind us that certainty is an illusion, and that the beauty of the universe lies not in its predictability, but in its depth. In that fragile space between observation and reality, between what we see and what is, Bohr found the heartbeat of the quantum world, a reminder that knowledge is not a mirror but a meeting. As the 20th century unfolded, Niels Bohr's ideas became the foundation upon which the towering structure of modern quantum mechanics was built. Yet the beauty of his vision was that it never stood still. Quantum theory, like the universe it sought to describe, evolved, shifting, expanding, and branching into new territories that even Bohr himself could scarcely have imagined. From the seeds of his early atomic model grew a vast forest of discovery. The generations that followed took his principles and carried them forward. exploring deeper layers of the quantum world, and though the mathematics grew more complex, the spirit of Bohr's thinking, the humility before mystery, the balance between logic and imagination, remained at the heart of it all. The decades after Bohr's discoveries saw an explosion of new ideas. Schrödinger's wave equations refined the behavior of the electron, transforming Bohr's orbits into fluid clouds of probability. Heisenberg's uncertainty principle expanded the idea of quantization into the realm of knowledge itself, showing that even the act of defining one quantity precisely blurred another. Together, these theories built upon Bohr's foundations and formed the complete architecture of quantum mechanics. It was as though Bohr had drawn the first sketch of a grand design, and others had filled in its intricate details. In laboratories across the world, the implications of Bohr's quantum vision began to unfold. Scientists discovered that the same rules governing atoms also applied to light, to energy, even to the vacuum of space itself. Quantum field theory emerged, revealing that the universe was not a collection of isolated particles, but a dynamic web of interactions, a continuous field where particles were excitations of invisible energy waves. Bohr's insight into quantization now appeared everywhere, in the vibrations of molecules, in the patterns of crystal lattices, in the faint radiation of black holes. The quantum world was not confined to the atom, it was the foundation of reality itself. Technological revolutions soon followed. Transistors, lasers, superconductors, all were born from the principles Bohr helped set in motion. The electronics that power our world, the communication systems that span the globe, the screens we look at, and even the tools we use to study the universe, each owes a debt to the quantum mechanics that evolved from Bohr's atomic model. His abstract ideas became the engines of civilization. Where once the quantum realm was a distant curiosity, it had now become the pulse of modern life. Yet the evolution of Bohr's vision was not limited to machines and devices. It also changed the way humans think about reality. The deeper scientists looked into the quantum realm, the stranger it appeared. Phenomena such as entanglement, where two particles remain mysteriously connected across vast distances, challenged every classical notion of space and causality. Experiments showed that particles could exist in multiple states at once, only deciding when observed. The universe that Bohr helped reveal seemed to whisper that reality was far more fluid and interconnected than anyone had imagined. Bohr's philosophical ideas also grew in importance. His concept of complementarity became a guiding principle not only in physics but in other fields of thought, reminding us that complex truths often require opposing perspectives to be fully understood. In biology, psychology, and even art, thinkers began to see echoes of Bohr's insight, that the observer shapes the observed, and that knowledge is built from interaction rather than isolation. His vision encouraged scientists to see the world not as a set of rigid laws, but as a living system of relationships, always changing, always incomplete, yet beautifully coherent. As quantum mechanics matured, it began to stretch beyond the microscopic into new frontiers: quantum computing, quantum cryptography, and quantum teleportation. These emerging technologies continue to carry Bohr's legacy forward, turning his abstract ideas into tools that may one day transform communication, medicine, and intelligence itself. The quantum computer, for instance, harnesses the strange dualities of superposition and entanglement to perform calculations beyond the reach of classical machines. Each step in this evolution is another chapter in the story Bohr began, a story of curiosity, courage, and the relentless pursuit of understanding. Even now, physicists find themselves returning to Bohr's philosophical compass when facing new mysteries. His caution against absolute certainty serves as a reminder that science is a dialogue, not a declaration. Though quantum mechanics has expanded far beyond his original framework, the principles he laid down continue to guide the journey. Bohr once said, "Every great and deep difficulty bears in itself its own solution. It forces us to change our thinking in order to find it." The ongoing evolution of quantum theory embodies that truth. From the earliest models of the atom to the quantum technologies shaping the 21st century, Bohr's vision has proven timeless. It grows and transforms like a living organism, branching into new forms while keeping its roots deep in the same soil of wonder. What began as a bold attempt to explain atomic stability has become the foundation of a worldview, one that sees reality as layered, probabilistic, and alive with potential. The story of quantum mechanics is thus not a tale of replacement, but of expansion. Each new theory, each new experiment, adds another layer to Bohr's vision rather than erasing it. His ideas remain the framework through which all others pass, the first light that continues to guide exploration into the unknown. In the dance of electrons, the shimmer of photons, and the hum of quantum circuits, Bohr's legacy endures. A reminder that knowledge is never complete, and that beyond every discovery lies another mystery waiting to unfold. Niels Bohr's vision did more than transform physics, it reshaped the future of humanity. From his pioneering model of the atom emerged not only a new way of seeing nature, but an entire technological civilization built on quantum principles. The invisible world he helped uncover became the foundation for the visible progress of the modern age. His ideas reached far beyond laboratories and equations, rippling through industries, inventions, and philosophies that define the way we live today. The quantized electron that once existed only in Bohr's imagination now drives the devices in our hands, powers communication across the globe, and fuels the computers that expand human thought. Bohr's vision became the bridge between abstract science and tangible reality, proving that deep understanding of nature can transform the world itself. In the early years after Bohr's discoveries, scientists worked feverishly to apply his theories. The structure of atoms, explained by quantum mechanics, led directly to the development of semiconductors, which became the building blocks of modern electronics. The transistor, perhaps the most important invention of the 20th century, could not have existed without the quantum understanding of how electrons move through matter. From that small switch of quantum behavior came radios, televisions, computers, and eventually the digital universe that defines the 21st century. Every pulse of electricity that flows through a circuit today carries a trace of Bohr's insight into quantized energy levels. Lasers, too, were born from this legacy. When electrons drop between Bohr's quantized levels, they release photons, light of precise, measurable energy. Harnessing that process led to the creation of coherent light, the laser beam that now reads our data, performs surgeries, measures cosmic distances, and powers global communication networks. In each flicker of laser light is the echo of Bohr's understanding that energy is not continuous, but comes in perfect, discrete steps. But the reach of Bohr's vision extends even further. In the field of medicine, quantum theory made possible magnetic resonance imaging, or MRI, a technology that peers deep inside the human body without harm. Quantum mechanics also guides the creation of radiation therapies that save lives daily. In chemistry, it explains the bonds that form between atoms, dictating the structure of molecules, materials, and medicines. The elegance of Bohr's quantized atom now safeguards health, fuels industry, and illuminates the very processes of life. Bohr's influence also touched the human mind. His philosophical insights into the limits of observation encouraged thinkers across disciplines to reconsider the relationship between perception and reality. Artists, writers, and philosophers found inspiration in his notion of complementarity, the idea that truth can appear contradictory yet still be complete. It became a metaphor for human understanding itself, reminding us that complexity and uncertainty are not failures, but reflections of deeper harmony. In this way, Bohr's quantum world became a mirror for the human condition, uncertain, paradoxical, yet profoundly ordered beneath the surface. The evolution of technology continues to prove the power of Bohr's foundation. Quantum computing, one of the most ambitious frontiers of modern science, operates on principles that trace directly back to his ideas. These new machines exploit the superposition and entanglement of particles, concepts that grew from Bohr's interpretation of the quantum realm, to perform calculations at unimaginable speed. Quantum communication, quantum sensors, and quantum encryption now promise to revolutionize how we process information, protect data, and explore the universe. Each step forward is a continuation of Bohr's original leap of imagination, the belief that by understanding the smallest scales of nature, we can reshape the largest scales of existence. Yet perhaps Bohr's greatest contribution lies not in technology but in attitude. His scientific philosophy taught generations that knowledge demands humility, that every answer opens new questions, and that cooperation is the true engine of progress. The collaborative spirit he fostered in Copenhagen became a model for international research, influencing not only physics but the culture of global science. His advocacy for openness, dialogue, and shared discovery laid the groundwork for the modern scientific community, where nations and minds unite in the pursuit of truth. As the 21st century advances, Bohr's legacy continues to expand into the cosmic scale. Quantum physics underpins our understanding of stars, black holes, and the origin of the universe. From the formation of atoms after the Big Bang to the behavior of matter in extreme conditions, every model of cosmology carries traces of his principles. The stability of the cosmos itself, the reason stars shine and elements form, rests upon the same quantized laws Bohr first proposed. In the quiet rhythm of atomic transitions, in the glow of starlight, in the pulse of digital circuits, Bohr's vision endures. He revealed that stability is born from restriction, that energy moves in steps, and that understanding requires balance between the known and the unknown. His work not only explained why atoms do not collapse but also why knowledge does not stop, it evolves, just as the universe does. Bohr's influence stretches beyond science into the essence of what it means to be human. His life's work reminds us that to explore the universe is to explore ourselves, that curiosity, doubt, and imagination are the tools through which civilization grows. From the electron's orbit to the quantum computer, from the glow of a distant star to the screen before our eyes, Bohr's vision continues to guide us through the mystery of existence. It tells us that progress is not merely the accumulation of knowledge, but the deepening of understanding. In every atom, in every spark of light, in every question that remains unanswered, Bohr's dream lives on, the eternal quest to see beyond the visible and to uncover the quiet order that shapes the universe.